Question 6.5 is about the different properties of logarithms. So here's a list of all the properties of logarithms. We are going to go over each of them individually, but I wanted you to have a list in one space, especially if you're using the slides for review. So let's take a look at how we can apply all these different properties. And I am going to go over each of them in detail throughout the course of this section. So my first property of a logarithm is a logarithm of 1. If I have log base a of 1, that equals 0 for any number a. Why does this work? Well, remember, logarithms are exponents. So if I convert this to an exponent, this is saying a to the 0 equals 1. And I know that to be true. Any number to the 0 power always equals 1. So if I have log base 2 of 1, that's 0. If I have log base 7 of 1, that's 0. If I have log base half of 1, that's 0. Next property I have is that if I have a logarithm with a base of a, then I have log base a of a is 1. Now remember, if I convert this to an exponent, this tells me a to the first power is a, and this is always true, right? If I have 7 to the first power, it's 7. If I have square root of 2 to the first power, it's square root of 2. So I'd have log base square root of 2 of square root of 2 is 1, and log base 7 of 7 is 1. Next, I have the power property, and the power property is this. If I have log base a of x to some exponent, r, that's the same as r times log base a of x. Let's take a look at this. So let's say I have log base 2 of 2 cubed, and I know that's going to equal 3 times the log base 2 of 2. Well, log base 2 of 2 cubed, that's log base 2 of 8, which is 3. That would give me 3 times log base 2 of 2, which is 1, so 3 equals 3. That's true, right? What this is saying is I can move that exponent to the front. So if I have log base 5 of 25 squared, that's the same as 2 log base 5 of 25. If I have log base 7 of x to the 10th, that's the same as 10 log base 7 of x. They're equivalent. So, friendly reminder that I want to say real quick is that the natural log of e is 1 because log base e of e is 1, right? And we already said that if I have a log base a of a, that's going to equal 1. So the natural log of e is 1, and we're going to use this property to solve quite a few exponential functions. So if I have log base 7 of 7 to the 29th, that's the same as 29 times log base 7 of 7, which is 29 times 1, which is 1. If I have log base 2 of 2, that is 1. If I have log base 2 of 8 cubed, I can move that to the front. That's 3 log base 2 of 8. Log base 2 of 8 is 3. 3 times 3 is 9. If I have the natural log of e square root of 2, that becomes the square root of 2 times the natural log of e, which is 1. So I'm left with the square root of 2. Now, here is a theorem for solving exponential equations using natural log, okay? The theorem is this: if I have y equals the natural log of e, that's the same as x equals e to the y, okay? And it's going to use this power for our e's to cancel out. This is the way it talks about it in the book. I am not going to do it this way. Here's what we're going to do. What we're going to want to do is we're going to want to take the natural log of both sides. Remember, if I take the natural log, I can go ahead and move my exponent to the front. Also, we have an equation, so what we do to one side, we got to do the other side. That gives me x natural log of e equals the natural log of 12. The natural log of e is 1, so I'm left with x natural log is equal to the natural log of 12. For this second problem, I have e to the 2x minus 1 equals 5. Again, I'm going to take the natural log of both sides. I get 2x minus 1 times the natural log of e equals the natural log of 5. I go ahead and am left with 2x minus 1 equals the natural log of 5. I add 1 to both sides, and then I can divide by 2. That gives me x equals the natural log of 5 plus 1 over 2. Next, if I have e to the x squared equals 200, I'm going to take the natural log of both sides. I get x squared, natural log of e, equals the natural log of 200. So I have x squared equals the natural log of 200. In order to get rid of that square, I'm going to have to take the square root. So x equals the square root of the natural log of 200. Note, I'm taking the square root of the natural log of 200, not the square root of 200. So I can't simplify this any further. The next two properties are the product property and the quotient property. So this says if I have log base a of x times y, that's equal to log base a of x plus log base a of y. So if I have log base 2 of 3 plus log base 2 of 6, that's going to be the same as log base 2 of 3 times 6, which is 18. I also have the quotient property. So if I have log base a of x over y, that equals log base a of x minus log base a of y. So if I have log base 5 of 35 minus log base 5 of 7, this would be log base 5 of 35 divided by 7, which is log base 5 of 5, which is 1. So this one I could simplify further, this one I could not. So let's go ahead and find the value of each expression. So if I have log base 8 of 2 times plus log base 8 of 4, that's the same as log base 8 of 2 times 4, which is log base 8 of 8, which is 1. If I have log base 6 of 9 plus log base 6 of 4, that becomes log base 6 of 9 times 4, which is log base 6 of 36, which is 2. If I have, oh my gosh, this is the example I did on the previous slide. I'm not very creative, you guys. If I have log base 5 of 35 minus log base 5 of 7, that's log base 5 of 35 over 7, which is log base 5 of 5, which is 1. If I have log base 8 of 16 minus log base 8 of 2, I can combine those to be log base 8 of 16 over 2, which is log base 8 of 8, which is also 1. Again, not very creative with my solution answers. So the next rule that we have is that the log of a power equals a product of the power and the log. So for example, if I have a log base a of m, that's going to be m. So if I have e natural log of 8, that's just going to give me 8. If I have 9 to the natural log of 9, 13, that's going to give me 13. If I have 4 log base 4 of 6 minus log base 4 of 5, I need to rewrite this as 4 to the log base 4 of 6/5, but that's still just going to give me 6/5. If I have 5 log base 6 plus 5 to the log base 5 of 6 plus log base 5 of 7, that becomes log base 5 to the log base 5 of 42, so my answer is going to be 42. The last thing I want to talk about, I think it's the last thing, is the change of base formula. So if I have log base a of m equals log base b of m, that is this log base a of m equals log base b of m over log base b of a. I'm taking my argument, I'm taking my base, and I'm changing the log. So I could also rewrite this as if I have log base b of a times log base a of m, that's log base b of m. So let's look at this example. If I have log base 2 of 6 times log base 6 of 8, that becomes log base 2 of 8, which is 3. If I have log base 3 of 8, which is log base 8 of 9, that becomes log base 3 of 9, which is 2. Now, with this change of base formula, we could also use the natural log or log base 10 in order to solve these equations. This is helpful because in older calculators, you only have natural log and log base 10. You couldn't do log base 2, you couldn't do log base 3, and so on. So I'm going to go ahead and show you how we would solve these problems. So I'm going to use the natural log. I'm going to take this to be the natural log of 89 over the natural log of 5, and you can use that to approximate your answers. So that would give me 2.7889. Now I also could have used log base 10, or I could have used log base 3, and I would have gotten the exact same answer. So for log base square root of 2 of the square root of 5, I'm going to use log base 10. So I have log square root of 5, so log of my argument, over log of my root. That would give me about 2.3219. Again, this is one way to help you in your calculator if you have an older TI-84 and you can't use specific bases of your logs. You can also use change of base to graph your formulas. For example, we could write this as the natural log of x over the natural log of 3, and it would be the same as log base 3 of x. So let's go ahead and go to Desmos. So here we are at Desmos. If I have to open this tablet up so I can type an equation, f of x equals log base 3 of x, here's my function. I said that was going to be equivalent to the natural log of x over the natural log of 3. And let's take a look at why that is. So look, here I have in blue using my change of base formula. Here I have in red using the original function, which is log base 3 of x. Let me also show you that this works as well for log base 10. Again, this is one way to graph these functions if you do not have specific bases in your graphing calculator, like mine, because my graphing calculator is ancient and was $5 on Facebook Marketplace. So here it is in green on base 10 using the change of base formula, blue using natural log and the change of base formula and our original function.